Okay, so now what we're going to do is we're going to look at rates and how to relate to concentration and time. As we said in the last slide, is the rate law basically finds that at some point in time, and what we want to do is look at a change in time, the concentration as a change in time. From the first slide we came up with is that the rate is equal, the simplest is that, so we have A going to B, so you can write the rate expression is minus A over change in A over change in T. But it's got to equal to our rate law as well, Ka. All right, so what we could do is that using calculus, okay, is what you end up doing is you get this equation here, the ln over the kt, and then go ahead and solve it, and then you end up getting these two equations here. All right, this equation here is expressing this equation in terms of as an equation of a line. Okay, and simply what you do is you so this is, remember, this is going to be ln of a0 over ln at, and then you remember for logs it'd be, this can also be written as ln a0 plus log of, that should be minus at, okay, and then you just subtract a0 from both sides, and then you get this, and then you rearrange it, and you can get this. Okay, so you don't have to worry about that, but that's how we get this equation here, is because of the rules of logs. Okay, and when we look at, if we plot an experiment, for instance, this will yield a straight line, especially if it's first order, and it'll be k will be a minus, it slopes down, and so minus minus it will give you a positive, and the intercept will be right here, be the log of a0, if we didn't know already. So let's say we just took the experiment here somewhere, then we could have figured this value up here. And that was for first order. For second order, we could write the equation like so. And then we end up getting this equation, doing using calculus. And then so the previous equation we had was it ln a t over ln a 0. Well, not just ln of equals kt. Okay, this one we get with this. And these will be both available to you. Okay, so this is what you would get when you plot. So for the previous one, you do the log of your concentration, it gives you a straight line. For this one, we do the reciprocal, you get a straight line. And that's kind of how you know if you get a straight line, you get from the reciprocal, second order. If you get a straight line from and it's going pointed up, then it's second order. If it's pointing down and you're using a log function, then you know it's first order. So let's how to determine reaction order using rates. And so that's what I just talked about. So so if it's linear, if it's first order, you take the log, or 1 over a is curved, I mean. So the log is, like I said, log is linear, and 1 of a is curved. And if it's second order, 1 over a is linear. Okay, if both plots are horizontal, then then it's zero order. Okay. So let's say we're given this data here, and you go ahead and plug it in, and let's see what it looks like in the next slide. And you get this. Okay. So so what you do is you look at the SOCL2, and you do use the data, and you take the log of the data and the reciprocal of the data and see what it looks like. And since it goes down with a straight line, and here it goes curved with this curve up, so you know it's going to be first order, because when it's log and going straight and down, then it's first order. Okay, no experiment. And here you go. Okay, we plug that, put this in our graph, come up with this. Now in this case, we take the log, and we can see it goes down, but it's not straight. Okay, but we take the reciprocal, and it goes up and it's straight, so we know it's second order with respect to HI. All right, so here's the problem. We're going to assume this is first order. We didn't tell you that here, but here it is. So here's our first order equation. Our initial concentration is 100, because it will say it's 33%, so we're assuming that 100%, and then this is 33%, so that's why it's 100 over 33, and then 21 days, but we want in terms of seconds per second. So go ahead and solve this, and then you'll end up with a 0.0528 per day. Notice, okay, we don't have units here, but it's a, and then we want to change that to seconds. So it'll be 1 day over 24 hours. Okay, and then get rid of hours, 60 minutes per hour, and then get rid of minutes, end up with seconds, and then so you get your days cancel out, hours cancel out, minutes cancel out, end up with per second, and you do the math, you end up with this value as the answer. For a first order reaction, what should be plotted in order to observe a linear relationship? Well, it's going to be the log versus time. If you did reactant per time, you're going to end up with a curve. It's going to be curved either first or second order, okay? Because, well, zero, you won't get any change at all. Well, actually, zero. If you did this guy right here, first order would still be, still go down. A second order would go down faster, but still be curved. And then for zero, be a straight line. So you're not going to get any information out of this one. This is going to give you second order. And we're going to assume we have enough information, so it's A. All right, the rate constant for second order is 2A to B, so we know it's second order. We're given the rate constant, and we're given the time, 2 hours, change that to seconds. So that's going to be 2 hours times 60 times 60, 7,200. And we know our final concentration is going to be 0.35. What we want to do is find our initial concentration. Plug everything in, solve for A0. Okay, remember when you do this, the simplest way to kind of do this is add, so here's your equation, add this value here, subtract this value here from both sides. Do your math. Okay, and then take the reciprocal of this value and then multiply it by a negative. All right, that's how I would do it. All right, I'm not going to solve for A0 before I do it. So I would do the math first. So I have 1 over A0. Do this math and then take the reciprocal of A0 and to the minus value. Okay, half-lives. Half-lives are how much of the material you have. So how long does it take to get to half of the material you started with? So let's say you started out with 100 of A, and then what you want to do is know how long does it take to get to B. Okay, and then so that's called the half-life. And so what we can do is simply solve for that. So this shows you how you do it. So we go ahead and do that, and we get the half-life of first order reaction is equal to, so the half-life is equal to log of 2 over the rate constant. Okay, so this is handy dandy. So and notice it's independent of concentration. All right, that's an important thing. Doesn't matter how much A you start out with. All right, so let's take, so again, A is independent of concentration. And here's an example. So if you start out with 2, 1, it took this much time, and that's called the half-life. And we call it decays. All right, and we use it not only in rates, but you often might hear in terms of radioactive material, which you'll talk about. If we talk about nuclear reaction, we'll talk about that. But it also applies to chemical reaction. Okay, so this is sort of a graph. So you start with A. So notice it's not linear. So so I don't know how many pieces we have here, but let's say you have 100. So if you have 100 here, it will take 8 days to go to 50. All right, now to get half of that to 25 also takes 8 days. So it's not, so you're not going, so it's not linear. So to go half of that, 12.5, is also 8 days, and so forth. Okay, so and then so essentially asymptotes here, where you constantly get smaller and smaller and smaller. So the next one would be 6.25 and so forth. Right. Okay, for half-lives of second order reaction. So second order rate equation, you look like the half-life equation looks like this. And notice now that the half-life is related to the initial concentration. Okay, so that ends this section on concentration and time, and I'll send you out a worksheet for figuring out rate constants using rate law, and also doing rates using concentration and time. So first part slide, so give you theory. Second, third, give you application. The next two slides get into actually what happens during the chemical reactions, and it's called the theory of the reactions and collision theories, and what are the components of making a chemical reaction take place, and so that's all the particles bouncing together, and then we'll actually be using the universal gas constant, because the universal gas constant is sort of the energy of particles, random particles. And then we're going to put that all together to figure out sort of how the rate of a chemical reaction is dependent on the concentration, how the particles bump into each other randomly, and their orientation. So in the first slide, we talked about those 5 different things that determine uh, the rate of reaction. And the 2 and 3, we just basically wrapped it up into 2, concentration and K, holding temperature constant. Now we're going to actually look at what's in K, what's in K, and also temperature. So we won't be using concentration much. We'll be using K, figuring what K is made out of. The other things like orientation, how the molecules hit each other, how fast they hit each other, and all that, and also implicating temperature with this. So that'll be our next slide. And then the final slide is kind of cool, is that it'll actually look at a chemical reaction and look at what happens to chemical as A goes to B. What happens to it. Like it might change. A might turn into something else, and then it turns into something else, and then it turns into something. Finally, it turns into B. And at each step, it might be happen at a different speed. Okay, and that's what the last slide. And that's really useful in terms of like looking at enzyme kinetics if you get into biochemistry. All right, so I'll send you out a worksheet to do with this. With the last 2, actually there will be part of that worksheet will include the material from here as well. Okay, so that's it for this slide. It's pretty short, but hopefully you got the thrust of it, and we'll put it together in your worksheets.